Hello class, welcome back to Control Systems lectures, and this is the fourth lecture under the second chapter that we are looking at, which is modeling in the frequency domain. In our last class, we were able to introduce the essential mathematical background that we need for this course. We looked at ordinary differential equations, Laplace transform methods, and partial fraction expansion. Something I need to mention, which I believe you need to also look at, especially in the notes that I sent you, is the complex number. You have to review complex numbers. It will help you also. It's part of the background mathematical knowledge that is needed for control systems. We also define transfer function, and also there is more materials on the notes with regards to transfer functions and block diagrams. We will deal with block diagrams much later in detail, but in the notes there are a few definitions and explanations on block diagrams. Please do go through those notes carefully. So what we'll be doing in this lecture is to develop the transfer functions of linear time invariant system. So LTI stands for linear time invariant systems. We're going to look at mechanical systems, both translational and rotational systems, and then we'll look at electrical networks, we'll look at electromechanical systems, and later on we'll be looking at how to linearize nonlinear systems. Control systems class for this particular class that we're doing focuses on linear systems. So for nonlinear systems, we need to linearize them, and that's where the linearization or to linearize nonlinear systems is very important. So let's start with the translational mechanical systems. Mechanical elements, usually we have three of them. These mechanical elements can be broadly classified with respect to whether the element forces are proportional to acceleration, displacements, or velocities. So elements can store and release kinetic energy, elements can store and release potential energy, and elements can dissipate energy. So these are the three broad classification of mechanical elements, and you'll soon see these three elements. So the translational mechanical systems can be modeled using the mass elements. These are the elements we're talking about now, the frictional elements or the spring elements. The basic variable used to describe the dynamic behavior of translational mechanical systems are the displacement, which is x in meters, the velocity v, meters per second, and acceleration, which is in meters per second square. And then we have the force, which is in Newton. So these are the variables. The basic variables you will use for the mechanical systems are the displacement, the velocity, acceleration, and force. Now let's look at the displacements and how they are measured with respect to some reference condition. So when you have a mass, you must indicate your reference condition so that you know that this is the initial condition, and if there is an applied force here and the mass moves through some distance, that distance will be measured based on the reference position. So reference arrows for the displacement, velocity, and acceleration of a given point are invariably drawn in the same direction so that the following equations can hold. So we don't indicate displacement in one direction and acceleration in a different direction. We indicate them in the same direction so that you can see that your velocity is the differential of the displacement and your acceleration is the differential of your velocity, which is the double differential of your displacement. So we indicate the arrows for the displacement, the velocity, and the acceleration in the same direction. So now let's look at the mass elements. So this is a mass element with force applied to it. Now this mass element, the force, if you remember Newton's second law, the force will be equals to mass times acceleration, which is mass times the differential of the velocity, which is acceleration, which is equals to m times a. The t in front of a and in front of v just tells us that this variable is with respect to time. So v with respect to time. And this will give us, it can be written as mx double dot. So this is displacement differentiated twice is equals to acceleration, or velocity differentiated once will also be acceleration. So any of these three actually means the same thing. And so this will be equals to the applied force. So simply, this is the F is equals to MA applied to this mass. The assumption is that the mass is constant with no relativistic effects. So the mass remains constant. It's not kind of compressing and expanding. It remains constant. Then we have the energy of moving and static masses. So these are the kinetic energy for moving bodies, and this is given as half mv squared. We all know this is known if you are taking the velocity in three-dimensional. So that will be v of in the x direction, in the y direction, and in the z direction. And then the potential energy is the mass times the gravitational acceleration times the height. So this is potential energy of the mass. Now let's look at the friction elements. Friction elements are elements with viscous coefficient or damping coefficient. So the viscous friction, which is a linear relationship between force and velocity in this case, you can see that you have the mass, which is moving on a fixed body, but between the two there is a friction that is taking place, and this is represented as V, which is Newton second per minute per minute. Sorry. This is Newton second per meter. This is the unit for the viscous coefficient. So this is how we model the mass on a fixed surface moving in this direction, where you have frictional force between them. So we used to model this for like dashpot, like the shock absorber, for example, and this looks like a shock absorber. You can see if you apply a force in this direction and in that direction, taking this as a reference point, so this will move at velocity v2 and this is velocity v1. So the force will be the viscous damper or the viscous coefficient or damping coefficient multiplied by the change in the velocity of the two ends, which is equals to b v1 minus v2. This will give us the force for a viscous damper is the viscous coefficient multiplied by the velocity. That is, if v2 is equals to 0, let's say we keep v2 fixed, then ft will just be b v1. Then we have here what we call the nonlinear friction elements. This is the column and drive friction, and these cases we will not be considering in this course, but they are non-linear. We will see this when we draw them in a graph form. You see that these are non-linear friction elements. Then this, when we have a mass with two rollers beneath, it shows that this condition is a condition where there is no friction at all. So in this case, you won't have any B viscous damping or viscous coefficient between the two because it is pure rolling, and so it will be no any friction coefficient. So friction elements or friction force always opposes direction of motion. Important for free body diagram. You must remember this. And then power dissipated by friction is the product of exerted force and relative velocity of the element ends. So it is immediately converted to heat and cannot be returned to the system. So when there is friction that takes place between two bodies, heat will be dissipated, and that heat is lost. It cannot be restored back to the system. If friction element is massless and a force is applied to one end, then a retarding force of equal magnitude and opposite direction is applied to the other side through the friction element. So we will get to understand this even more better as we go through to some of the examples. So this is a plot of the velocity and the force curves for the three different friction elements. This is the linear friction element, viscous friction, which is the one we will be dealing with in most cases. And then you have the column friction. So you see this is like a step function. So it is non-linear. And then you have the drag friction, which is this friction, which also you can see is non-linear. And this is what you have, for example, of a submarine moving under water. The next element is stiffness element. So we've looked at the mass element, we've looked at the friction elements, now we'll look at the stiffness elements. These are characterized any mechanical element undergoing a change in shape, provided only that elongation and applied force are related algebraically. So like spring. So we're talking of a spring, for example, you apply the force and the relationship between the force and the elongation has an algebraic relationship. So d0 here stands for the initial distance, and so when you apply the force, you have x2 minus x1, where d0 spring length when no force is applied. That is what d0 is. And then your force will be the k, which is the stiffness constant, or spring constant, multiplied by the change in of the spring. This is how you find the force. This is the equation for the force. On del x is x2 minus x1. And you can see in this case you have your reference point here. If one end is fixed and you pull and you apply a force on the other end, then your force will just be kx. So your force will be k multiplied by the displacement x. And the unit of k, or the spring constant, is Newton per meter. F and x both point in the same direction, and since x is defined as elongation, F is defined as a tensile force. If it's defined as a compression, then the force becomes a compressive force. So if the stiffness element is massless and a force is applied to one side, then a force of equal magnitude and opposite direction is directly exerted on the other side through the friction element. Potential energy is stored in a stiffness element that has been stretched or compressed. And so when it's released, it releases the energy. And this is the equation. The work due to the potential energy is a half k times the change in its of the extension square. In your textbook, you'll find these relationships. We have a spring, viscous damper, and the mass. And this is the force-velocity relationship. So if you try to relate the force with the velocity, and in this case for spring, we know that F is equals to kx, but x then is the integral of velocity, and that's why we have k integral of velocity, because this is force velocity. But if you now go to the force displacement relationship, you have kx, where x is a function of t. The impedance, which is like the inertia that needs to be overcome for the stretching of the spring, is the spring constant. And for the viscous damper, we also have F is equals to FV. Now, I must say that I use B in place of F subscript V. In your textbook, you'll find F subscript B. Just remember that this can be replaced with a B, which is what I use for viscous damper. So, and this is the force displacement relationship, and the impedance will be BS. So if you replace F of V with B, so it will be BS. Then you have the mass relationship, and here again you have the the reference point for the extension, and you apply your force. So in this case, F is equals to m dv dt, which is your force velocity relationship, where dv dt is acceleration. So this is ma. And then if you have the force displacement relationship, which means you want to replace your dv with using displacement, so if it is square x over dt. And for the mass, the impedance is ms squared. There is a note here that the following set of symbols and units is used throughout this book. Now, Ft is newtons, Xt is meters, and V is meters per second. K is your Newton per meter. Now, we have replaced this with a B. The textbook uses F subscript V, but in our class, we will be using the small letter B, which is Newton second per meter. So let's look at a few laws that have been used to develop these equations. The Lambert's law is the reformulation of Newton's second law, and so Newton's law stated the sum of forces exerted on the element is equals to m dv dt, or ma. This is acceleration, and the reformulation is bringing the inertia in there and saying that the sum of exerted forces minus the force that you need to overcome the inertia in order to move is equals to 0. So the Lambert's law is the reformulation of Newton's second law. So all he did was to lump the two in the inertial force with the external forces and say that is equals to 0. So you see that the summation of the exerted forces is 0. Interconnection law 2, law of reaction force, which is Newton's third law, says accompanying any force of one element on another, there is a reaction force on the first element of equal magnitude and opposite direction. So you can see that you have two elements together, and when you look at the force that is applied to these, the force exerted by the mass on the spring is in opposite direction, and the force exerted by the spring on the mass is also in opposite direction, but they're both equal. So how do we obtain a system model? We represent the variables in terms of x and its derivatives. So you have x for displacement, velocity, the differential of x to give you velocity or x dot, and then acceleration, which is the derivative of the velocity, or if you take the derivative of the displacement twice, will give you x double dot. So these are the symbols we use for modeling. The second thing is the free body diagrams. You've done free body diagrams in dynamics, and so in this class you know already what it means when we talk about free body diagrams. So element laws are used to express all forces except inputs in terms of displacement, velocities, and accelerations. And then you must be very consistent with your signs, and in general, forces must be added as vectors. So these are the rules for obtaining a system model. Then if you have a parallel combination of springs and dashpots, this can be replaced with the equivalent of this. So the K equivalent for this arrangement is K1 plus K2, and the B equivalent of this parallel system is B1 plus B2. So I told you that I will be using B instead of that F subscript V, so that's what we have here. Now, this is an example to find the transfer function x. This is a transfer function equation, that is xs over f of s, so which means this is already Laplace transform for the system that is shown below. So you have this system is a mass, spring, and damper combination on a fixed floor. So this is fixed. This can be, if you put it right side up this way, this can represent a vibration damper for buildings that are in earthquake prone areas, so that when there is a shaking, these dampers and springs will absorb the vibration and the building will just swing but not collapse. And also we can use this for machines foundations, so that when the machines are operating, they vibrate. The vibration absorbers will absorb the vibration, that it is not transmitted to the foundation of the building. Or this could also be a model of road vehicle suspension system. So you see that a simple mass spring damper relationship can represent different models already in the physical sense. And we'll do some examples as we go on with this class. But let's go back to our question. The question is for us to find the transfer function for the system that is shown in this figure. So what do we do first? We draw the free body diagram. And notice that the free body diagram is all around the mass. So if there is one mass, it's a 1 degree of freedom system. If you have two masses, it will be a 2 degree of freedom system. So in this case, we have a 1 degree of freedom system. So we draw the mass and indicate the forces. So here we have F, which is the applied force in this direction. So our spring, the force due to the spring, will tend to pull this for mass backwards, and the damping coefficient will also pull it in the opposite direction. So you have the free body diagram here. This is your applied force, and this is the force due to the spring, this is the force due to the damper, and this is the force due to the mass itself, or the inertia of the mass. So if you now write the equation that is taken using second law of Newton, you have summing all these forces here, m dx squared over dt, which is this force plus that force, will be equals to the applied force. Now this is still in the time domain, and for us to find the transfer function, we need to do a Laplace transform of this. So if you assume that initial conditions are 0, which means this mass, we applied the force from rest. So mass was at rest, and then we apply the force. In that case, this will be Laplace transform to ms squared x of s. This will be Laplace transform to bs x of s, and this will be Laplace transform to kx of s. So this is equals to f of s. You can see again that when we Laplace transform, the small letters become big letters, and that's the difference when we, that's the convention when we do the Laplace transform. Then from this equation, the transfer function, as we know, is x of s over f of s. So if you take x as subject here, and then you find x of s over f of s, you have 1 over ms squared plus bs plus k. So this is your transfer function for this system. And then in block diagram representation, I told you the transfer function is usually in the box. So you have your transfer function here, and you have your f of s, and the way you read this is f of s multiplied by whatever is in the box is equals to xs, and this you can see from the equation here as well. So this will be the block diagram. This is what the question wants you to find out. This will be the answer to the question. And this is what we refer to as your transfer function. All right, the next is to find the equation of motion for a 2 degree of freedom mechanical system shown below. Now you can see that mechanical systems is quite simple. I started with the mechanical system because you are mechanical students. We will also do electrical systems, of course, but I would like you to just try your hands on this and see if you can come up with the block diagram for this system. And when we meet in class, I will then solve this, and we will go through it, and you will be able to see if we are on the right track. So thank you very much for this introduction to mechanical systems.